Welcome back to STEM Talk with STEMencounters. My name is Saifin Jwani, the CEO and founder of STEMencounters. And if you've read our website, it's our website. If you've seen another episode of the podcast, and if you've looked at our Instagram and social media posts, you know who we are and what we do. We're a student-led nonprofit, 501c3, known as STEMencounters, dedicated to teaching, expanding, and encouraging STEM knowledge within everyone. We specifically focus on material science and engineering, a passion of mine, something that's nonprofit, and this podcast is centered on. We do a lot of other aspects of STEM in our nonprofit, but this podcast is centered on material science and engineering. And it's something that's very interesting and something that we go very, very deep into. So definitely stick around for something that we have a very, very interesting episode today. So if you want to learn more about us, I said before, STEMencounters.com. We have online courses, event planning, blog posts, information about STEM, and so much more coming out. Our Instagram is at STEMencounters. Yeah, definitely go on our website to learn more about us, who we are, what we do, and the new events that you can learn from, because learning is the best thing that we can do. So today we have actually a very special guest here, Professor Farrauto, a professor from Columbia University, and he's going to talk about the research he does there, but the research and the work he did in the industry, because he also worked in industry, what material science and engineering aspects he's done throughout his days and his work, and just the things that he's done for the world. So without further ado, let's get right into the STEM. So today on STEM Talk with STEMencounters, we have a very special guest, Professor Farrauto, a professor of professional practice of Earth and Environmental Engineering in the Department of Earth and Environmental Engineering at Columbia University. Thank you so much for coming on the podcast, Professor Farrauto.
Thank you very much.
So give me some generalities about yourself. What do you do and why do you do it?
Well, I've been doing engineering and science now for a long time. I worked in industry prior to coming to Columbia for 44 years. I worked mostly in the environmental area, especially utilizing catalysts to convert toxic emissions to harmless emissions. I've worked on many chemical processes to improve the production of various materials by modifying the catalyst or modifying the process. And then in the year 2012, after 37 years with a company that was called Engelhart, and then eventually was purchased by BASF, which is the largest chemical company in the world. They're a German-based company, where Engelhart was American-based in New Jersey. So BASF bought us in 2006. And at that time, I was already adjuncting teaching at Columbia. And Columbia had been asking me to permanently retire and come over and effectively be on their permanent staff. But I had an obligation to stay in order to try to help with the transition from Engelhart to BASF. And that was a very interesting transition. So I stayed 6 years. During that time period, I was made a vice president of research. So I was engaged in automotive catalysis, hydrogen, fuel cells, or a wide variety of different kinds of materials. And then when I joined Columbia in 2012, I worked on pollution abatement. I worked on various methods of generating hydrogen. And I also worked, obviously, right now on the whole concept of CO2 capture and conversion to useful products, because we have a climate change issue that must be addressed.
Yeah, the climate change issue is something that you work on a lot, and it's something that's very important for us to.
Yeah, there's quite a bit of different technologies. We think our technology is rather unique, and perhaps at some point during this discussion, we can talk about it a little bit more. I did send you that one paper, but there's a lot of interest in the work that we're doing, and I'd like to share that with you and your students and your friends.
So, where did you go to college and why? And when you went to college, what was your major?
Okay, I went to Manhattan College in the Bronx. Even though it's called Manhattan College, it's actually located in the Bronx because at one time it was in Manhattan. And as Manhattan was becoming more commercialized, I think the school felt the need to move to areas where there was a little more room. And at that time, there was a lot more room in the Bronx. So Manhattan College is in the Bronx, and I did my bachelor's. and I did that in chemistry.
Okay.
And then I had a very strong desire to move on to get a PhD. So I went to Rensselaer Polytechnic Institute, which is in Troy, New York, upstate New York. And again, I majored in chemistry. And after 6 years of working on automotive catalysis at a company called Corning, that you may have heard of, it's a New York State company. It's actually located in Corning, New York. In 1970, the US government passed the Clean Air Act, which required that automobiles meet certain emission requirements to remove toxic materials because the health of the nation was being jeopardized. So Corning began to work on catalysis.
Mm-hmm.
And even though I had never done any work in catalysis in graduate school, which is common, that you do something different, I got involved very heavily in developing catalytic materials. But Corning wanted to use what we call base metal materials: copper, chromium, manganese, nickel. And one of the things that I did that ultimately led to me leaving Corning was found that there were inherent difficulties with using these materials because they were poisoned and they didn't have the thermal stability as what would be required in an automobile emission, because the temperatures are dramatically different. The exhaust contains a lot of different components that can damage the catalyst. So the alternative technology was being developed by a company called Engelhard, and that was using precious metals, platinum, palladium, rhodium, that are very expensive and very rare, but they worked for the automotive catalysis.
Okay.
So I proved that the base metals wouldn't work, and then Corning said, okay, well, we're not going to do this anymore. And by then, I was so excited about catalysis that when I was offered a position at Engelhard as a group leader, and I wanted to come back to the New York area. I'm from New York originally, so I wanted to come back to New York, and this was a company in New Jersey, in Islip, New Jersey, or Edison, New Jersey. So consequently, I took that position, and 37 years in the same building, just changed the name of the company in 26, and that is, it became BASF. And as I had said earlier, I worked in many, many different disciplines, but mostly focused on the environmental area. So it was natural that I move into the environmental engineering department at Columbia.
Yeah.
But even though I was trained as a chemist, I'm in the engineering school. And that's a good example of how when you come out of school, you end up learning new things and doing different things. And what happened was, because so much of industrial work is applied, I was using many engineering principles that I hadn't studied, but I was using them to help commercialize products.
Mm-hmm.
So now I'm much more comfortable actually in engineering principles and engineering teaching and research than I am in chemistry.
So how did you eventually go and pick the field of earth and environmental engineering? And how did you?
Because of the background. I mean, I had worked for a company that specialized in the environment.
Yeah.
That company, actually, Engelhard, developed the catalytic converter that's in your cars all over not only the US now, it's pretty much all over the world. So we are a major supplier of the catalytic converters. And that was initially for gasoline. And then we moved over to diesel. And we had quite a bit of technology in developing catalytic materials to control diesel emissions, which is even more complicated than the gasoline. So the environment has always been part of my profession.
Yeah.
And recognizing the importance of it as climate change has appeared, it was natural for me to want to stay in an environmental engineering department. But my students are all trained, my PhD students, master's degree students, most of them are trained in chemical engineering. Mm-hmm. So I'm kind of a hybrid of a chemical engineer with a chemistry degree. But as I said, you learn to do many different things, especially when you're working in industry.
So go into more about your job in industry. What did you do there? And you mentioned the catalytic converter. How did you
Sure. Well, I was the manager of a group that was doing what we call materials characterization, mm-hmm. which meant that all of the different materials that were being investigated needed to be characterized. Certain properties needed to be understood. And these are fundamental properties of catalytic materials. Also metallurgical materials, because I worked in that area as well. So I was managing the materials characterization. That gave me a broad view of all the different types of things that were happening with Engelhart. Engelhart, I might mention, specialized in precious metals, platinum, palladium, rhodium, looking to make new products out of these materials. So it was natural that they would study these materials for the catalytic converter. So I became very knowledgeable, if you may, about the use of precious metals for many different applications. And then over the years, I started moving into some aspects of gasoline, automobile catalysts, but the biggest challenge was the diesel. And in 1990, I started working with, I had a team of about 18, 19 scientists and engineers, and we developed the first diesel oxidation catalysts that went into many of the trucks in the US. And then we continued to develop that beyond 1994 for passenger cars, which were very popular mostly in Europe and Asia, not so popular in the US. But now there are diesel vehicles in the US because there's catalytic converters that allow cleaning the emissions. So I worked very heavily in that whole area of environmental catalysis. I also did work in stationary abatement, that is power plants that generate, excuse me, power plants that generate toxic emissions, chemical facilities. So all of these things usually end up using precious metal catalyst materials. And then in my final years at Engelhart, then into BASF, it was mainly on the hydrogen economy, of which I spoke about at the lecture series that you attended.
Yeah.
And then naturally, I brought a lot of that with me when I went into industry. And a lot of the students at Columbia liked the fact that I worked in industry, so I give them a different perspective than those professors that never went on and only stayed in the academic circles.
Yeah, I think that your perspective is definitely needed. And when you mentioned about the hydrogen economy, it's something that's, I mean, that's very interesting. What we're moving towards.
Yes.
So when you went to Columbia, when you eventually made that transition, how was that like when you were going from industry to kind of more of a professor and research type of thing?
Yeah, well, I mean, obviously I very much enjoyed teaching, and then I did have a pretty substantial research group. I think the one big difference was industry is dictatorial.
Okay.
There's bosses that make decisions and you have to adhere to them. You are very much involved in current technologies where there's markets, because the goal of an industry is to make money, hopefully while making products that are useful. Whereas in the academic circles, although some products go commercial, most of the professors are interested in writing publications, which is fine. But I like to write publications that are practically and can be potentially used. So that's the big difference. I think that in the academic circles, commercialization is not a goal. It's nice, but it's not a goal. Where in industry, it is. And then there's this whole issue of tenure that you probably heard about, where professors, after so many years, are guaranteed a job, continuing to teach and do research. And in industry, you're never guaranteed anything. You could lose your job if all of a sudden there's a crisis in the economy, or if you happen not to be meeting the goals technically or managerially of the company. So your job is always in question when you're in industry, whereas once you're tenured, it's not. So I'm not in a tenure track at Columbia. I have contracts, but my contracts have always been renewed because I think they appreciate the fact that I'm bringing some different disciplines, plus I'm bringing money into the department as well, which is always a critical issue. In industry, most part, the company supplies the money in order to develop a product.
Now, when you talked about how in industry it's all about money, but in like at Columbia it was all about more of like publications and more of that. So did that idea of like money over anything else in industry kind of shift your way towards Columbia?
Um, well, I mean, I went to Columbia mainly because I had given a seminar there when I was working at Engelhart.
Mm-hmm.
And I gave the seminar in the Earth and Environmental Engineering department.
Mm-hmm.
And it was obvious when the department chairman sat in on my seminar, he said, I was talking about the catalytic converter and things like that. And they realized that they don't have anything that deals, or anybody that deals with air pollution control. So for that reason, they invited me to be an adjunct where I could teach courses in emission control and air pollution control. They specialized in many other things. They specialized very heavily in water analysis, water hydrology, waste to energy, things like that. So I offered a kind of a different perspective, and that more or less completed the portfolio of truly being earth and environmental, where you deal not just with the earth, but you deal with the air as well.
Mm-hmm.
And that's part of what I've been doing ever since I joined.
Yeah, that's so important. So on the Columbia website, your research areas include materials, nanoscience, sustainable humanity, and with an emphasis on energy. So what made you research these areas in particular?
Because of the need, I mean, it became very obvious that global warming was a major challenge,
Mm-hmm.
that fossil fuels were eventually going to become no longer available. They were limited supply, and now there's a lot more energy that people are finding, a lot more oil that people are finding,
Mm-hmm.
a lot of natural gas. But I felt as though there was a need to move away from fossil fuel and more towards a hydrogen type economy, or an economy that was generating their power from something that would not be polluting the air or that would not be creating climate change.
Yeah.
So that was kind of why I moved in the direction of hydrogen, because I felt as though that was a very interesting way of substituting fossil fuels.
Mm-hmm.
That technology is actually moving along. You don't hear much about it in the US, but it's very popular in Japan and Asia, in Europe. But I believe eventually we'll see much more activity of that here, as we're now learning that we could use renewable energy to generate hydrogen.
Yeah.
Hydrogen doesn't exist naturally in the environment.
Mm-hmm.
That's why we call it an energy carrier. It's not itself like oil that you can immediately burn, or natural gas. Hydrogen you have to put energy into making hydrogen.
Mm-hmm.
Therefore, the whole concept, and this was my talk, was that ideally you could make hydrogen from water just by supplying renewable energy, which means that we are now approaching an all hydrogen economy where we're no longer using carbon.
Mm-hmm.
So that's kind of the ultimate goal that we'd like to be at. But there is no hydrogen infrastructure now. There is no way of broadly generating hydrogen economically. But eventually, when that technology is fully developed and people know how and efficiently generate hydrogen, the question is, how do we distribute hydrogen to the energy sectors where it's needed?
Yeah.
Because right now we have pipelines that contain natural gas. We have service stations that contain gasoline and diesel. There aren't any of these available for hydrogen. So that's why my last slide in my presentation was the future is going to be for young engineers, scientists, and policy people to move forward towards replacing fossil fuels with something like hydrogen.
Yeah.
Certainly using renewable energy sources.
Mm-hmm. Yeah. Renewable energy is very important. And then the hydrogen whole idea is something we're going to touch on a little bit later, but something that's very, very important. So on the Columbia website, your description says that your research allows students to see catalysts applied to problem solving. So your group studies dual function materials for capturing carbon dioxide and catalytic conversion to reusable fuels, thereby decreasing greenhouse gas emissions.
Right.
So what does all of that mean? And tell me the process of how that works.
Well, a flue gas is the exhaust from a power plant. Now, most power plants in the New York area effectively use natural gas, which is mostly methane.
Hmm.
It's much cleaner than coal. Doesn't have the ash, doesn't have the sulfur content. So, and because it already contains 4 atoms of hydrogen, that means that when you burn natural gas, you produce carbon dioxide and you produce water. And those are of a lower energy than the original methane. So it means you liberate a lot of heat.
Yeah.
So that's the reason why many power companies have moved away from coal and now use natural gas. Now, natural gas, although it produces half the amount of CO2 per energy unit as does coal, it's about a 2-to-1 footprint of coal to natural gas, it still generates carbon dioxide.
Hmm.
So our technology is an inorganic material that is composed of a adsorbent that it's an alkaline material because carbon dioxide is acidic.
Yeah.
So you have an acid-base reaction, which you
Hmm.
learn about in chemistry.
Yeah.
And the carbon dioxide, being acidic, can adsorb onto our adsorbent material. And that's what we mean by capturing the carbon dioxide.
Okay. Okay.
Now, in concert, we also have a catalytic metal in the same material as the adsorbent. So we have 2 functions then. We have an adsorption function of carbon dioxide and a catalytic conversion function to make methane. So therefore, we call it dual function. It's got adsorption and catalysis as part of its duty cycle.
Hmm.
Now, the methane that's burned makes CO2. We then would like to take hydrogen that's produced from renewable sources, electrolysis of water, using photovoltaic devices, of which I spoke about in my lecture.
Yeah.
And that hydrogen can then be used to remake the methane from the CO2.
Hmm.
And then we take that methane and we go right back into the power plant. So we're cycling the carbon and making the overall cycle carbon neutral.
Hmm. Okay.
And we're preventing carbon dioxide from being emitted into the atmosphere. And thus, no carbon dioxide, and that means no contribution to greenhouse gas. One other thing, too, is because we can remake the methane catalytically, and you need a catalyst to speed up this reaction,
Yeah.
that means that the plant needs to import less natural gas in order to burn, because we're remaking it.
Yeah.
That means less fracking.
Okay.
That is the way in which most of the natural gas now, especially in the US, is made available. It's produced by pumping chemicals into the ground, which is environmentally not a sound way of doing things.
Yeah.
And then they pump the methane out. Well, now by this technology of CO2 capture and reconversion back to methane and recycling the methane, it means that not only are we not producing carbon dioxide for the global climate change effect, but we're also remaking the methane, which means less methane needs to be extracted from the earth, and thus we're trying to preserve the earth to a greater extent.
Yeah.
So that's the whole concept of the dual function material. We operate at about 300 degrees centigrade. And the reason we do that is because that's about the temperature of the exhaust from the power plant. So we don't have to add any energy. So we can do everything in one temperature. We can absorb the carbon dioxide. We then add the hydrogen. And in the presence of the catalyst, the absorbed CO2 reacts with the hydrogen, and catalytically it's reconverted to methane, all at the same temperature. So we're not heating and cooling them things. We're doing everything at one unified temperature.
Yeah, I definitely think that's a benefit in not adding any external heat.
Right.
Yeah.
Yeah, that's a bit of that brings me to another issue that we'll talk about a little bit later on, called direct air capture, which has that problem. Okay, so we'll get to that perhaps a little bit later on, whenever you'd like.
Yeah. So you've done a lot of work in developing new processes to decrease methane emissions from natural gas fueled vehicles using novel technologies.
Right,
So
right.
how did you do this?
Well, this was one of a great PhD student that I had who now works for a major catalyst company. It happens not to be BASF, but another catalyst company.
Mhm.
And part of the reason was that that paper was so beautifully done. And the additional paper, the one that dealt with methane, there were 3 separate papers, all right, all of which dealt with the automotive emissions, but only one of them dealt with the methane emission. But she actually developed a way in which we could remove the methane from the exhaust, right? Because right now, the catalyst technology does not remove the methane that's present in the exhaust. And therefore, it's not a regulated gas, even though it contributes very significantly to greenhouse effects. At the time when we were doing this work, it's unregulated because it's so difficult to burn and to oxidize that it's considered inert to photochemical reactions that lead to smog formation and some of the toxicity. So methane is not regulated by the Clean Air Act, but we developed this technology in anticipation that perhaps someday the regulations will be where they are going to remove methane or have to remove the methane from the exhaust, because when the Clean Air Act was passed, which was 1970, nobody was even thinking about greenhouse effects. And methane did not contribute to any of the photochemical reactions that were leading to toxicity of the air. And therefore, they just said, all right, because it's difficult, we'll just leave it. Well, now I think that's a material that's going to have to be addressed. And we're addressing that with different catalysts, different processes. And the work that we published on that methane abatement used a renewable fuel as a means by which you could remove the methane.
Yeah. Hopefully, like some policymakers can introduce this act similar to the one.
I think they will, especially when we have a new administration that's much more friendly towards the environment. I think that there'll be a lot of movement towards the so-called new green economy. It'll be slow, but all of these things are slow, but they're revolutionary.
Yeah. So I've seen that you are very interested in the hydrogen economy. In fact, you mentioned it before. So go in a little bit more depth. What is this? And can you tell us more information about the hydrogen economy that we should know?
Yeah, well, the hydrogen economy, obviously it contains no carbon. So that's one of the big issues. And if you take the hydrogen and use it in a fuel cell, you change the way in which we now generate energy. You're familiar with a battery.
Yeah.
Fuel cell is nothing more than a battery, except that we continuously add externally hydrogen and air. Hydrogen is oxidized at an anode, air is reduced at a cathode, you generate electricity, but you have no mechanical steps. You have no engines as you do in the case of a steam turbine or in the terms of a gasoline internal combustion engine.
Yeah.
So the very fact that you have a mechanical step in between the chemical reaction, which is eventually combustion, and then the final generation of power, that mechanical step limits the thermodynamic efficiency of your process. Now, you guys haven't had thermodynamics yet, but it is a very, very important aspect of how energy and heat are interrelated.
Yeah.
And engines like pistons, which is an internal combustion engine, or turbines, as in a steam turbine, or any mechanical device, it extracts the energy so that your efficiency is much lower. In the case of a hydrogen-based fuel cell, you don't have any mechanical steps. And furthermore, you're not burning anything because you're doing everything electrochemically. That means you're not generating all the pollutants, you're not generating CO2, you're not generating nitrogen oxides, all of the toxic materials that are produced as a consequence of burning a fuel. So the fuel cell is an intimate part of the hydrogen economy, and that's why I linked the two of them in the lecture that I gave.
Yeah.
By the way, you have the slides, I assume, right? Professor Avila made the slides available?
Yeah. So I definitely will share those slides with in the comment section of this podcast for anyone to see. Very, very interesting slides. I recommend anyone to look at them.
Very good.
So you've won many awards, such as the Sayapeta Lectureship Award by the North American Catalyst Society. So is there any award that you're most proud of, and what research do you think allowed you to get this award?
Yeah, well, it was not research so much, but I got a teaching award at actually Columbia in 2016. The students gave me a teaching award that was sponsored by the alumni at Columbia. So I have to be as proud of that, because when you get something from students, it's real.
Yeah.
When you get other awards, sometimes it's more political. Now, I did make some contributions based on some of the things that I did, so I don't want to say that I didn't have some accomplishments, but many awards are more politically oriented than would be a student award. The students don't lie. Students do not play politics. If they think you're a good teacher and they've learned something, they give you an award. So having that teaching award was one of the great things for which I'm very proud. I actually got it from another university as well. I used to do adjunct teaching 30 years ago, and I also got a teaching award from another university, but the one at Columbia is the most recent one. That was in 2016.
Wow. Yeah, students definitely, I think, have an impact, or people have talked.
Well, we do student evaluations. That's part of where it comes from. After each course, the students are asked to complete, and this is all anonymous, so you don't know the name of the students, except that they're students in your class. They rate you. They rate you in terms of your preparation, in terms of your delivery, in terms of the course material, how much they learned. They rate you based on the type of exams, your availability to help them when they need help. And that's really the main reason why I wanted to work in Columbia or go to a university after industry, because I really wanted to share some of the things that I learned in industry with students, and they appreciate it.
Yeah. So let's talk about more of your research that your team does at Columbia in carbon dioxide capture and catalytic convergent fuels. So we mentioned this a little bit before, but in an interesting paper that I read and that you shared with me titled Dual Function Materials for Carbon Dioxide Capture and Conversion Using Renewable Hydrogen, discussed how the accumulation of carbon dioxide emissions in the atmosphere is a very, very big problem. And it's very, very energy intensive to capture carbon dioxide. So, and then would you like to mention something?
Yeah, the reason I say it's energy intensive is the state of the art, the best technology that's available right now for capturing carbon dioxide is to take a liquid material that's an amine. It's a nitrogen containing organic material. And if you have to take the exhaust, cool it all the way down to 40 degrees centigrade, and it absorbs the carbon dioxide. So you have that big change from 300 degrees. You got to cool it all the way down to 40 degrees centigrade. You could use some of that heat, and that's fine. But then to remove the CO2 from the amine, you have to reheat the material, and that's very energy intensive. Because in the process of reheating it, not only do you evolve the carbon dioxide from the amine, but the amine is present with a lot of water present. And if you heat the amine up to about 120 degrees centigrade, you also vaporize a lot of water. And that's a very energy intensive thing. So you are requiring a lot of energy to remove not only the CO2, but consuming a lot of energy to simply remove the water. And then you have the carbon dioxide. Now you have to decide, what do I want to do with it? So that means that what they do typically, or what is proposed, is do we take that carbon dioxide, we compress it, and we transport it, and then we have to decide whether we want to dump it into the ocean, we want to dump it into the ground, so-called carbonization, carbonates, or can we make some really good chemicals from it? And that's really would be a nice way to do this is to make something that's useful out of that carbon dioxide.
Mhm.
But the technology is not very good right now to do that.
Yeah.
The beauty that our technology has is that there is technology that takes carbon dioxide and hydrogen and makes methane.
Mhm.
So our advantages that we have is that you don't have to add any energy, okay? The technology exists for converting carbon dioxide back to methane.
Mhm.
So we don't have to transport the carbon. We do everything at the same site where we're generating the CO2.
Mhm.
We just have to bring the hydrogen into the plant.
Yeah.
And that's the so-called hydrogen infrastructure. We need
Okay.
pipelines that can transport hydrogen from renewable sources like water, electrolysis, et cetera, and then
Mhm.
bring that hydrogen in. That's what's missing right now.
Yeah. Yeah. And then that paper went into the dual function materials, which is something that you work with a lot, and how that can capture carbon dioxide from an emission source in the same reactor and convert it to a synthetic natural gas.
Right, exactly.
Mm-hmm. So I know you mentioned a little bit about dual function materials, but is there anything that you didn't mention that you want us to know about and why you work with it so much?
Well, as I had mentioned to you in an email, we've advanced our technology since then.
Mm-hmm.
We have new materials. Well, they're not that new. They're alkaline materials, but we don't use calcium as we did in that one paper that you said
Yeah.
there. We also have reduced the amount of ruthenium, RU, which is the catalyst material, because it costs about $9 a gram. So it's much more expensive than other materials,
Mm-hmm.
but it works very well, and it can be recovered and recycled.
Yeah.
But we've reduced the amount of ruthenium from 5% down to about 1%.
Mm-hmm.
So that's good.
Yeah.
So that's kind of where we are right now in our work with the power plant. We've also done aging studies where we've exposed our material to a typical exhaust from a power plant, and
Mm-hmm.
we've recycled it to make sure that the material is stable.
Yeah.
Now, the one thing that now we need to think about, besides the power plant application, is how do we take the existing CO2 that's in the air out?
Okay.
Let's assume that by tomorrow, magically, we stop using fossil fuels.
Okay.
That means we're not generating any new CO2 in the atmosphere.
Yeah.
Let's assume that we're using hydrogen or some other resources of energy, photovoltaics, et cetera, wind energy. Then that means that we will not be generating new CO2, but we still have 420 ppm of CO2 in the air that is creating climate change right now.
Yeah.
So even though we may not generate new carbon dioxide,
Mm-hmm.
what's going to happen is we have to take the carbon dioxide out of the air.
Yeah.
Air is at room temperature.
Yeah.
Or ambient temperature.
Yeah.
In the summer, like now, it could be 90 degrees or 80 degrees. In the winter, it could be 10 degrees. So that means now that the DFM is going to work at 300 degrees centigrade. That means we have to heat up all the air that we bring in to the DFM material, which is too energy intensive.
Yeah.
So now what we're doing this with the Department of Energy grant, and we're working with an engineering company, is we are trying to develop materials that will function at lower temperatures. That
Okay.
includes the absorption and the catalysis.
Mm-hmm.
And I have 2 PhD students right now working on that. And I'm probably going to be bringing in what we call a postdoctoral student, a student that's already finished their PhD, and therefore they don't have to take courses and all the things that PhD students have to do. And that student can work with our engineering partners to see whether or not we can further develop this technology. This is called direct air capture, DAC.
Yeah.
And the carbon dioxide content is very low. It's only 420 ppm typically.
Mm-hmm.
Whereas in the case of the power plant, it was 75,000 ppm. So big difference in the amount of CO2 that you're dealing with. So when you're dealing with small amounts of material, it introduces other physical issues, things that we call mass transfer. Again, I won't get into that in too much detail, but that's a very strong engineering and reactor design concept.
Yeah.
So that's kind of what we're working on right now under this DOE grant.
Yeah.
But we also are still working to some extent on some fundamental things that we've learned about the DFM material that we'd like to investigate more on a mechanistic point of view.
Yeah.
So we have both practical work and we have some fundamental work just to give better understanding of how the DFM works.
Wow. Wow. So how does this paper eliminate, like your approach in this paper, eliminate energy intensity in carbon dioxide emission? You mentioned it a little bit,
Right.
and not to add external heat, but go a little bit more in depth.
So that's the main energy intensity. In other words, as I had mentioned to you about the liquids,
Yeah.
you have to heat them up
Yeah.
to remove the CO2, and you want to recycle the amine material,
Yeah.
and that tends to deteriorate with time.
Mm-hmm.
But also because you have to heat it up from 40 degrees up to maybe 120 or 130 degrees, you're not only breaking the bonds between the carbon dioxide and the amine, but you're also vaporizing all that water.
Yeah.
So the very fact that we don't have to do that step means that we're saving energy. The very fact that we're generating the methane at the same site where it was generating CO2 means we don't have to transport the CO2 by truck or by train. And then we don't have to dispose of the CO2 because now we have a product that we can make directly from it. So that's why it's very energy intensive to remove CO2 by the current technology. And that's why I think we got the award from DOE, because they felt as though our technology had promise not only for the power plant, but also for the direct air capture.
Yeah. Yeah. I definitely do think it does have promise. So I want to talk about another section of the paper that I found interesting, the material synthesis portion.
Sure.
So the paper talked about how dual function materials were prepared by incipient wetness impregnation. So can you tell us about what that is and how that process contributed to DFM?
Yeah, incipient wetness is a very convenient technology used by industry. We now use it pretty regularly in academic circles as well to simplify the preparation of a material and without having to do a lot of analysis on the material. So if you just take a porous material like a sponge, okay, and you soak up some various chemicals, you're not going to know how much of a given species may have absorbed onto the surface. So the incipient wetness method means that you take a porous material, which in our case, and was mentioned in the paper, is alumina, Al2O3. Alumina is like an inorganic sponge material. And the incipient wetness means we determine what the water uptake of that material is. In other words, how much water is required to saturate the porous material. Once we know what that is, and we know what the weight of the material is, we can dissolve our components in that precise amount of water. And then when we put the solid porous material into that solution, it will suck it all up. And therefore, you no longer have any remaining liquid, and all of your species are absorbed onto the material. And therefore, you don't have to do additional analysis, and you don't have a waste stream of water that contains things that you now have to dispose of. So we call that incipient wetness. And it's used heavily in industry, especially in the precious metal industry, where you don't want to, you want to make sure that all of the material gets impregnated into the spongy inorganic material. The incipient wetness method allows you to do that.
Okay. Okay. Wow. So that whole system is it is very important. It seems like to that
Yeah,
whole.
by the way, after you do that, you then dry it to
Okay.
get rid of all the moisture, and
Mm-hmm.
all the inorganic material
Yeah.
will stay, the non-volatile material will stay in the porous material. And then you heat it to a higher temperature in order to do some conversions to the desired species that you want in the porous material.
Okay. Okay. So moving on from this paper, is there any publication that you're currently working on that is beneficial with this carbon emission problem that you're trying
Yeah,
to?
I mean, that's the one I mentioned. Again, all of these questions I answered. So if you have trouble with the transcription of this this video,
Yeah.
in the message that I sent you, there's a lot of these answers.
Yeah.
We have just submitted a preliminary paper on direct air capture of
Mm-hmm.
carbon dioxide using DFM technology.
Okay.
That is currently under review.
Uh-huh.
And what the review process is that, again, it's an anonymous process. They usually send it to 3 experts that work in the field,
Mm-hmm.
and they ask for criticisms of the paper.
Mm-hmm.
And it's a very, very good process. I do a lot of reviewing of other people's papers, but our papers then get reviewed, and the reviewers ask us questions, or they say, we need to clarify something in the paper, or maybe they don't agree with something that we say. So that paper is under review right now in a very prestigious environmental journal.
Oh, so is that whole process very like intensive?
Yeah, it's a very, usually you have at least 2, and most of the time 3 reviewers.
Okay.
It gets sent to a journal. That editor then decides who would be the right people to review it.
Mm-hmm.
And then they review it, and it's a very detailed process. And as I say, it helps us see what weaknesses we may have had in the paper.
Mm-hmm.
So it's a very valuable thing to make a better paper.
Yeah.
Sometimes they'll say the paper is not good enough to be published.
Wow.
And that's very disappointing. But generally that hasn't happened to us, but I've recommended certain papers not be published because I didn't think that they met the minimum goals of the particular journal.
Oh, okay. Wow. So I attended one of your talks recently. It was an amazing talk, but you discussed something that I want to bring up. So, and you mentioned in the podcast so far that we're moving towards a hydrogen economy, and that means our residential heat and power will be powered through a fuel cell system.
Mm-hmm.
And this fuel cell technology will also be used in our vehicles.
Right.
So go into that. How does you already told us a little bit how it works, but how is it being integrated in the world?
Right. Well, as I had mentioned, one of the problems we have right now with the hydrogen economy is we don't have pipelines of hydrogen. What we do have, and what industry uses, is natural gas pipelines. You can take natural gas, which is methane, and through a variety of catalytic steps, you can convert it to hydrogen.
Yeah.
So therefore, while we're waiting for the hydrogen infrastructure to be built, we'd like to be able to use fuel cell technology. But fuel cells require hydrogen. You cannot operate a fuel cell with methane directly. You have to convert it to hydrogen. So we could use the existing infrastructure in your home. Your home probably uses natural gas. Okay. Our home uses natural gas. Many companies, buildings, large facilities, many of them use natural gas because the pipeline exists. So you can take the natural gas from the pipeline, bring that natural gas into your home, and in the basement of your home, you can convert that methane to hydrogen. Now that sounds crazy, but you are effectively reacting methane with steam. And steam contains hydrogen. Methane contains hydrogen. Okay? So therefore, you can envision a process by which the methane can be converted to hydrogen and you make some CO2.
Mm-hmm.
That's the downside of doing this way, is you're still making some CO2.
Yeah.
Okay? But you can use this technology while we're waiting for the infrastructure to be built. And because the fuel cell is so much more efficient,
Mm-hmm.
you end up generating less carbon dioxide than if you burned it,
Okay.
the methane.
Okay.
Secondly, you don't generate any pollutants if you use a fuel cell, because effectively you're not burning anything.
Yeah.
Fuel cell operates like a battery.
Mm-hmm.
So that means then that in the fuel cell, in the basement of your home, you can generate your own electricity. And there's also heat that's liberated during this process.
Mm-hmm.
This is part of the thermodynamics that I don't want to get into right now because you haven't had that yet. But
Yeah.
you do generate electricity and you generate heat. So you could
Mm-hmm.
use the electricity to operate your computer, your TV, your washing machine, your lighting. You can use the heat to make hot water.
Wow.
Okay? So that's the so-called combined heat and power residential application for hydrogen fuel cells,
Mm-hmm.
using natural gas as your source of hydrogen.
Mm-hmm.
Now, for the vehicle, you can't do this because it's too complicated to do this on a vehicle. So you need to store hydrogen in the vehicle that will then operate the fuel cell, that will generate electricity, that will give you an electric car. Okay? Because the fuel cell will generate electricity that you will use to propel the vehicle. Instead of using a piston and an internal combustion engine, you will not be burning anything. You'll simply be using the battery or the fuel cell as a source of electricity.
Mm-hmm.
And that electricity operates electric motors that are positioned on the wheels. And the electric motors then allow the wheels to spin as a result of receiving the electrons from the fuel cell.
Yeah.
So that's an all-electric vehicle, but it's different than the Tesla or some of the other vehicles that simply use batteries and just simply discharge the battery directly.
Mm-hmm.
That battery has to be charged up periodically.
Yeah.
And the charging process is very long. It's about 30 minutes. Whereas with the hydrogen, if you have a hydrogen service station available,
Yeah.
you can replace the hydrogen that you've used in the same time as you would use for filling up a gasoline vehicle.
Mm-hmm.
So there's a fast turnaround.
Yeah.
The problem is we don't have hydrogen service stations available.
Yeah.
I showed you a picture of some in Japan. There are some throughout the US, but not as ubiquitous as gasoline or diesel.
Mm-hmm.
So this is another problem. You have to build a whole new infrastructure, not only of the pipeline, but of service stations so that vehicles can get hydrogen.
Oh.
You may have recognized, if you've done any traveling, there are small charging stations for Tesla-type vehicles.
Mm-hmm.
And certain stops, like if you're on the highway and there's a rest stop, they'll often have a hydrogen charging station there. You pay a certain amount of money, you wait 30 minutes, and it'll charge up your battery.
Yeah.
So they're building the electric infrastructure, but we still need to build a hydrogen infrastructure.
Mm-hmm.
There are a lot of them in Japan because there's a lot of fuel cell vehicles there. There's a lot in California,
Mm-hmm.
but not nearly as many as there are gasoline stations right now.
Yeah.
So the good news is this is what engineers are going to do and scientists in the future.
Okay.
They're going to be moving these technologies towards commercialization.
Mm-hmm.
That means we need more engineers, we need more scientists, we need policymakers that can make sure that the hydrogen is properly priced,
Mm-hmm.
and that hydrogen is safe enough to operate with,
Yeah.
and the regulations as to what's required. So it's a very rich future for a new infrastructure associated with non-fossil fuels like hydrogen and the all-electric type of vehicles.
Yeah. So that's very, very important. Hopefully everyone caught that what we're moving towards and what's actually been tested in Japan, this whole hydrogen system.
The hydrogen, there's a lot of hydrogen vehicles around. I showed you some pictures in the lecture. They're usually for lease. You can get about 325 to 350 miles of range on a tank full of hydrogen. And then, as I said, once there's a hydrogen service station available, you can fill up in a few minutes. Also, you can generate hydrogen in your home using the natural gas and then generate your own electricity and heat. Think about what that means in a hurricane. Now, we just had a storm and a lot of power went out, okay, because trees fell on the power lines. Think if you had your own ability to generate electricity in your home, you wouldn't be subject to that problem. So think of the advantages in storm-related areas where we no longer have a central power plant, all these overhead wires that have to deliver the electricity. There's a lot of power loss in the transmission of the electricity. And more importantly, you can generate your own electricity and heat in your home. So you're independent of the power companies. Then you think about the politics of all of this and the lobbies and all the groups that are no longer interested in this because it means that their jobs are going to change or their business will no longer be. Think about all of the oil companies. If we're not using oil or we're not using natural gas directly, if we can use hydrogen, all right, that is generated by renewable sources. So you can see there's a resistance to this by existing businesses. So that's why we need to understand the policy side of things.
Yeah, definitely. And so in this world of material science and engineering, many are working on to solve this prominent issue of like the carbon emissions and this hydrogen economy that we're moving towards. So I wrote a recent blog post that kind of talked about how gas membrane materials have been made to decrease carbon emissions. So what do you think about this?
I guess I wasn't sure I understood what they meant by this. There are materials that will permeate one gas and not the other. And those are generally what we call membranes, okay? It's like the membranes in our body. My guess, and you would have to correct me on this, is that what they're probably suggesting is that when you have a flue gas that contains CO2, nitrogen, oxygen, steam, etc., if you have a membrane that only allows carbon dioxide to permeate, then you can separate out the membrane from the various gases, and therefore you now have essentially clean CO2. But you still have to ask the basic question, what am I going to do with the CO2? I don't want to dump it in the ocean because it's acidic, it'll destroy fish, it'll destroy a lot of our aquatic life. Do we want to bury it in the ground? I'm not sure that's a good idea. Do we have processes by which we can convert carbon dioxide to other useful products? There are only a couple products that use carbon dioxide, one of which is urea, that's used for farming, for fertilizer. The other one is in beverages. Soda and beer all use carbon dioxide. There's also a use for carbon dioxide in what's called enhanced oil recovery, where you take pressurized CO2, you pump it into the ground, and what that does is it dissolves some of the rock, and it releases more natural gas and releases more oil. That's called enhanced oil recovery. But what we're doing now is pumping stuff into the earth, and this can create problems such as earthquakes, which is what's happening in the fracking operations. So I think one of the things that I think makes our DFM so unique, at least for the power plant application, is we don't have to be worrying about sequestering CO2. We're going to remake it into methane, and that means less of the environmental damage due to fracking operations. And we're no longer liberating CO2 to the atmosphere, in impacting climate change.
Yeah. So I think you talked about some research that you thought was interesting in the oil, you just mentioned, but is there any other astounding research in your field that you have read and you think is revolutionary?
Well, I mean, people are trying to develop catalysts and processes to take carbon dioxide and instead of making methane, make a more valuable product, a very unique chemical. Methanol is one that's getting a lot of attention.
Yeah.
And that is, can you take carbon dioxide using renewable hydrogen and make methanol? Because methanol has some uses. Can you make ethanol? Can you make gasoline?
Yeah.
But all of these things, ultimately, we're still involved with carbon, and that gasoline is going to be burned, and it's going to be generating CO2 again.
Yeah.
So there's a lot of different work that's going on, but they all require major inventions and major breakthroughs. I had not heard about the membranes.
Yeah.
You're not talking about the MOFs, are you?
No, I'm not talking about MOFs. It's more of a, so what I read was that they use fluorine atoms into membrane materials, and it improved the carbon capture and separation performance. That's what
by the way, the membrane that's used in the fuel cell is something that's called Nafion, and that contains carbon, fluorine, and chlorine. So it's a fluorinated carbon material. But I think there are membranes that can separate CO2 from other gases. But they have to be very stable. To these different gases.
So for the future, how do you want to see material science and your field specifically evolve?
Well, obviously, I'd like to see this climate change issue addressed in a way that we can move away completely from fossil fuel, and maybe the carbon that we have in fuel we can use to make medicines or very specialty materials. But the idea of burning a fossil fuel really is not, I think, the best way in which to preserve the earth. So I think material science is continuously used. Catalysis is used in the chemical industry, petroleum industry, alternative energy. Clearly, it's used in the environmental industry. So I think material science will continue to play a role in everything, from the production of pharmaceuticals, to the production of useful chemicals. Hopefully, as we've indicated, even in the fuel cell is a material science technology that uses nanomaterials. So I think that material science is really the key to our future.
So before we wrap up this interview, is there any final comments you want to make to anyone who's listening, who's watching?
Well, the one thing I want to mention is that I'm very pleased that young people like yourself are doing what you're doing. As I had mentioned to you earlier, I think we need more of our American-born people, young people, to migrate towards engineering and science. While we still bring in immigrants into the country that also contribute strongly, but we don't have enough of our native-born going on and staying in engineering very long. Many of them are trying to make a lot of money. They go into business, they go into investment banking. So having more of our young people stay in the technical field to develop, whether it be computers or to develop new membrane materials or to develop nanomaterials or whatever, I think this is really one of the things that I'd like to see. That's why the whole concept of new engineering for students, is a critical area, I think, and we'd like to see, certainly more of that. The STEM technology that you are proposing right now, not only should you get an engineering degree or a scientific degree, but get a career in that. Because it's very rewarding to see something that you develop go commercial. I mean, whenever I see a vehicle, I think about the catalytic converter that I worked on. So it's very rewarding to see that. I'd like to see some some people that do the same with the climate change. Maybe we'll do a little part of it, but I think that would be the best message I can give to young people, and that is that they stay in science and engineering and not always go for business or wherever you're going to make a lot of money. Scientists don't make a lot of money. They make a good living. They don't make as much money as investment bankers, but it's a very rewarding field.
Yeah.
I think it's part of the Engineering for Humanity, which is one of the goals of our Columbia Science and Engineering departments.
Yeah. And science is definitely needed in this world.
Absolutely.
So thank you so much.
We see it right now with the virus, right?
Yeah, yeah.
I mean, we see the scientists that are working on vaccines, that are working on therapeutics.
Yeah.
I mean, science is everywhere.
Yeah.
And it doesn't get enough attention, I think, that it needs and deserves.
So that was a very interesting talk by Professor Farrauto. He talked a lot about carbon emissions. He talked a lot about the hydrogen economy. He talked a lot about dual function materials. Something that's very crucial for our society today, as I said before, young scientists need to rise up, as something that we need to start moving towards, something that we need to work on, how we can use material science and engineering for our world, to better our world. Because these outputs, these things that we can see our effect on, is life-changing, and it will change our world for the better. So, as I said before, if you want to learn more about us, watch more episodes, definitely I encourage you to watch more episodes. Go to STEMencounters.com, Instagram at STEMencounters, YouTube channel STEMencounters. This is on this podcast on YouTube, Spotify, Google Podcasts. Listen to us, learn about material science and engineering. It's a very, very important topic in our world. And definitely just learn more about STEM. Go to our website. So thank you for coming on the podcast. Thank you for listening. Thank you for learning. And we'll see you in the next one.